This time we have an object on a horizontal surface again, but it is being pulled by a force F, whose direction is given to us from the vertical direction. Let's write down everything we know. We know the mass, we know alpha, and we know the magnitude of the force. All right. So the system is initially at rest, then it's going to be subjected by the force F applied at the corner, and that will cause the block to move towards the right with a non-zero acceleration. So, purpose of the game is first to obtain all the forces magnitude acting on this block. The second is to obtain its acceleration, and then we're going to go back to kinematics and figure out some of its kinematics property. So the first thing that is being told, that we're being told, is that the system is being accelerated along the horizontal, obviously towards the right. That means acceleration is right here and it's not zero. Based on this, which Newton's law do we have to use? Oh, I'm sorry, yellow is not very useful. If the acceleration on zero and towards the right, which Newton's law do we have to use? The first, the second, or the third? Excellent, obviously the second. So we know we're going to use this law. Perfect. We're looking for normal force acting on the block and its acceleration, so obviously the block is going to be our system. So let's identify all the forces acting on the system. First one that comes to mind, the weight, always down. We know the mass, therefore we will know everything about this force. Second on our list, normal force. This block is in contact with the horizontal surface, therefore there must be a normal force perpendicular to that surface, which implies that the normal force is vertical, and this force acts on our system. Hence, it's not only vertical, but it acts up. Therefore, N is up. Third, is there any pulling or pushing? In this particular case, we're being told that this block is being pulled by force F. So obviously F is here, acting on our system. Since no mu_s nor mu_k are given to us, we ignore friction as the previous problems. Perfect. Let's rewrite this so it's nice and clear. I'm going to represent my block by a zero-dimensional point and draw all my forces from that point. W, N, and F. Next stage. Let's pick a coordinate system. Now the big difference between the previous case and this case is the acceleration. If you have no acceleration, the trick is, as you pick your X and Y, make sure that you pick, whenever possible, either your X or your Y axis along as many forces as possible. If you have a complex system with a lot of different angles, we will see that later on, then ignore that rule and use another rule, which is pick X and Y such that most of the angles given to you are defined from either X or Y. This will allow you not to have to combine angles and do a bunch of tricky geometry. If the system is accelerated and you happen to know the direction of the acceleration, like in this case, and in 90% of the case you will, the suggestion is to pick either X or Y in the same direction as the acceleration. And I will justify why as we write the equations. So in this case, the acceleration is towards the right. Therefore, I'm going to pick positive X towards the right. And Y perpendicular. Y could be up, could be down, who cares? The important thing is I have decided to pick my positive X into the same direction as my positive acceleration. Last step. I have all my forces, all my label, my coordinate system. I need to figure out all the direction of all my forces with respect to my coordinate system. This should ring a bell. We're back to chapter 2. Remember, one of the questions on several of those quizzes is to ask you what is the method for you to express a force in componentation. Here it comes back. The first step was identify the direction between your force and either X or Y. In this case, since alpha was provided to us with respect to the vertical, and I've decided to pick my Y along the vertical, obviously, the direction of F is between F and Y. Done. Because now I'm in very good shape to express F in componentation. I use again the same method as I've asked you to provide it in the quiz. Now that you have identified the direction between F and Y, then you're going to identify the right angle triangle, which is the triangle between Y and F. Draw those little vectors, and then be able to identify who's the adjacent, who's the opposite, which one is going to be sine, which one is going to be cosine, and then you're going to check the direction of your vectors and change the signs appropriately. Perfect. So let's do this. Let's apply Newton's second law. Two-dimensional problem, therefore this one gives us two equations. First, I need to express the x component of f. Back to chapter 2, this should take us 10 seconds. If it takes us longer than 10 seconds, go back to chapter 2 and repractice those. In this case, it will be f sin alpha. Positive. Let's express the y component of f. If one is sine, the other one must be cosine. And they're both positive. Perfect. Let's go through n. The x component of n is obviously 0. But the y component of n is the full vector. And then the last one, wx, is obviously 0 again, and its y component is negative mg. Okay, so that was just chapter 2. Now let's bring back the physics. We have to complete that equation by adding ma. And that's where the advantage of picking positive x along the direction of motion will come into play. Since I've aligned x, my positive x, to be at the same direction as my positive acceleration, then my entire acceleration is in my x direction. Hence, there is no acceleration perpendicular to it. Therefore, a y is 0. So this trick of choosing the positive x along the same direction as the acceleration will allow you to have at least one 0 in one of the two equations and the entire a in the other. If you pick an x-axis or y-axis which is neither along the acceleration, then you're going to have to convert and project your acceleration vector the same way as you do forces. So you may have a cosine on the top, a sine on the bottom. They may be positive or they may be negative. That's just too much work. So just by being clever and picking whatever axis in the same direction as the acceleration, it will simplify your algebra. Because having to solve a 2x2 with a 0 somewhere is always nice. Okay, so let's look at this. We have two equations. Before you solve for anything, go back to your high school algebra. You can only have two unknown at most, because otherwise you can't solve it. So always make that check, because if you end up looking at your equation and realize, uh-oh, I have three unknown, then you know you should stop. Don't waste your time solving it. You need more equations. So in this case, f is given, alpha is given, m is given. Therefore, the only equations, the only unknown in those two equations are a and n. Now that we have clearly identified the fact that we have two unknown that matches the number of equations, now we can solve it for sure. We know there's going to be an answer. In this case, solving this is trivial. We can solve for n first, for example, and I'm going to get mg minus f cosine. As you can see, the magnitude of the normal force is not just the weight anymore. And we can plug values. And we can solve for a from the first equation, and we end up with f divided by m sin alpha. Done. The rest is just easy, just math, just algebra. So I usually always do everything analytically. if you don't like it, feel free to plug numbers at this stage. Plug your numerical value, obtain numbers. If that makes your life easier to solve for it, do that. Do whatever method you feel the most comfortable with. I don't really care, as long as your answer is accurate. However, if you would like to give me your analytical answer as you answer, like this, that's perfectly acceptable. I will take this as a correct answer. Okay? Now, the next question is calculate the magnitude of the object's velocity after it has moved by 3 meters. Hey, back to kinematics. Okay, so what's given to us? The distance that it has moved by. So from here to here is given to us. Obviously, that's a distance, x. So they're giving us x is equal to 3 meters. We were being told that the system was initially at rest. So V0 is 0. So, from the basic equation of motion, obviously the motion is taking place in the x direction only. And in the x direction, we now have a non-zero acceleration. If we pick the origin of a coordinate system at t is equal to 0, and our object is going to move by a distance 3 meters, then my equation of motion are nothing else but x is equal to v naught t plus x naught. Is that correct? Let me write them all down. V naught x plus a t. And the last one, as usual, so which equation can we keep? Which equation cannot be used? Let's review kinematic a little bit for the test on Thursday and Friday. We're looking at the horizontal direction that we call x, and we've just calculated the acceleration. Excellent. We knew one. Perfect. Do we have an initial velocity? Obviously no, because we started from rest, right? Do we have an initial position? No, if I put the origin at initial time. Bang! Now let's look at our nice simplified equation. One is gone. And that's what we have. Easy. So, now the question is, what is the stupid question? Calculate the magnitude of the object velocity after it has moved by 3 meters. So is there an equation that involves a velocity and a position? Sure enough, the last one. Therefore, we can use the last one and solve for A. The velocity in the x direction will be square root of 2ax. And obviously, the velocity will be towards the right. Therefore, we're going to keep only the positive direction. And this becomes 2f sin alpha divided by m times x. And again, we pick the positive number. And then we plug numbers. Okay? Similarly for the last one. Calculate the magnitude of the object velocity 10 seconds after it was pulled. Well, obviously, magnitude of the object velocity, we're looking for v. The condition is t, therefore, second. Hence, the last part will be f over m sin alpha times t. And that's it. So now we can do all the kinematics problem. But first, we don't have to be respected by a stupid free fall situation where A was always 9.8 and always down. Now we can use Newton, obtain the actual acceleration, which can be in any direction. And now we have a justification for the value of that acceleration, and we can go back to chapter 3 and 4 and redo all the kinematic type of problems now in any plane with any acceleration value. And we know now what created that specific acceleration. That's the power of Newton's law. Newton's law offers us a mechanism to predict the source of the acceleration of a system. Every time you apply force, it will create an acceleration. And the last thing about Newton's second law is all you have to do is calculate the net force, and the acceleration vector is going to have the exact same direction. And magnitude will just be the net force divided by m. We can divide this by m because in classical physics, m is always positive and always real.